The title of my presentation is Life, the Multiverse, and Everything. And this is, of course, a reference to Douglas Adams' work, Hitchhiker's Guide to the Galaxy. And I want to begin with a quote from that book. In the beginning, the universe was created. This has made a lot of people very angry and been widely regarded as a bad move. So throughout human history, we've been kind of obsessed with trying to determine what the nature of the universe is, how it started, where it's going. And I guess that's why a lot of you are here, is because it's an interesting topic. I find it fascinating. And a lot of this presentation comes from this book, A Universe from Nothing by Lawrence Krauss. So I highly recommend this book. It's really good. There's an audiobook version, which is also very good. It's narrated by Lawrence Krauss. Cosmology has changed a lot over the years. Centuries ago, we had this model of cosmology. The Earth is the center of the universe. The various planets and the sun are orbiting. The distant stars are fixed to this celestial sphere. So this was what dominated our view of reality all the way up to the 1500s. Now today, we have a very different view of what the universe is like. We've got, of course, the planets orbiting the sun rather than the Earth, but also our sun is just one of 300 billion within the Milky Way galaxy. And our galaxy, of course, is just one of 170 billion in the entire universe. So our view of the universe has really changed from a few centuries ago. But more than this, I'm going to go into some speculative territory here and say maybe the rabbit hole goes even deeper. Maybe our universe is not unique. Perhaps there's even more than one universe, and we're part of a vast multiverse, if that's the case. So this is speculative, but I'll present some reasons why this might be the case. So if you go outside at night in the city, you'll see something sort of like this, very disappointing in a way. It's only maybe a dozen or so bright stars, a couple dozen maybe. So you can't really see much. If you go far enough away from the city, you get a much better view of the sky, thousands of stars, and you'll see this subtle band of light across the sky, which of course is called the Milky Way. What you're seeing is the Milky Way galaxy edge on, so you're looking through the bulk of the galaxy from this suburban part of the Milky Way, one of the spiral arms. And all the stars you see are pretty much in a local neighborhood of the Milky Way galaxy. If you go back a century ago, this was the view of cosmology. Our universe was thought to be just the Milky Way galaxy. It's hard to believe, but that was the entirety of the universe just a century ago. And not only that, the universe was thought to be static. It was thought that the universe wasn't changing over time, that it had always been that way and will always be that way. At the time, for example, the Andromeda Nebula, as it was known, was thought to just be part of the Milky Way. It wasn't realized that this was another galaxy even. Things are about to change. It started with this man, Albert Einstein. This is a photograph of him in 1912. He was 33 years old. There's also a page of his manuscript that was recovered after his death in 1955. He was 76 years old then. So it's a really fascinating manuscript because it shows his thought process as he was developing general relativity. The general theory of relativity equates the curvature of space with the matter that's contained within that space. And you can think of it this way. Matter tells space how to curve, and curved space tells matter how to move. So that's sort of a general overview of what general relativity means. You can see it graphically this way. Imagine light coming from a distant star, traveling through space, and here I've represented space with this two-dimensional plane. It's kind of hard to imagine what three-dimensional curved space would be like, but it's easy to imagine what two-dimensional curved surface is like. If there's no mass in the way, that space is flat, and we get this flat plane, and the light beam travels in a straight line. But if we introduce some massive object like the sun into this flat plane, it'll actually curve space, so the light beam now will follow a curved trajectory as it passes by the sun. And this is exactly what was done in 1919 to try to prove whether relativity is true or not, is to observe a star that's near the sun, and it was found that the light deviated just the right amount, just in perfect agreement with the theory of general relativity. So after this point, this is when Einstein became actually famous. It was when his theory was confirmed by this experiment. Now there's a problem, and Einstein realized it soon after, in 1917, because his theory wasn't consistent with the then theory that the universe was static. His theory predicted that gravity was a universally attractive force, and therefore a static universe would eventually collapse. it was in manifest disagreement with what was thought to be the truth then. Instead of deciding that maybe his equation was correct, he decided to introduce a fudge factor. He added a term to the left-hand side of the equation, which we call the cosmological constant. It represented a repulsive force that acted at large distances and counterbalanced the force of gravity. In the scale of the solar system, this repulsive force would not be measurable, but over the scale of the galaxy, it would come to dominate and it would oppose the force of gravity and allow for a static universe, so Einstein thought. We'll get back to this later. Things have been changing, though, in cosmology, and in particular, one of the major problems in astronomy is we have difficulty measuring the distances to stars. And this is why we didn't know that there was multiple galaxies in the universe. So this woman, Henrietta Swan Leavitt, made a key discovery. Her discovery involved Cepheid stars. Now, Cepheid stars are stars that vary their brightness over time. So what Leavitt discovered was that those Cepheids that had a longer period were also intrinsically brighter. They had a higher luminosity. And the Cepheids that had a shorter period, they had a lower intrinsic brightness. So this is very useful because if you have two stars that have the same period, and one of them appears to be brighter than the other, then you know that the brighter one is actually closer. This gives us a way of judging how far stars are. And unfortunately, Leavitt's work would probably qualify her for the Nobel Prize, but she died at the young age of 53, and so she was never nominated, never received the Nobel Prize. But this man, Edwin Hubble, did use her work. Here he is operating the 100-inch Hooker telescope, which, when it was completed in 1917, was the largest telescope in the world. When Hubble took Leavitt's work and estimated the distance to the Andromeda Nebula, he found that it was 2.5 million light years away. Now compare that to the diameter of the Milky Way, which is only 100,000 light years. It's obvious that this object is way outside of our galaxy. And in fact, it's a galaxy in its own right, and it deserves the name galaxy, so it was renamed the Andromeda Galaxy. Hubble didn't stop there. Not only did he want to know how large the universe was, and of course this enlarged our view of the universe tremendously now that we know that there's other galaxies. He wanted to know how those galaxies were moving with respect to us. And he can do this too, because if you take light from a star and you break it up into its spectrum using a prism, you'll find that it's got these lines, these dark lines in the spectrum, which are absorption lines. So this is caused by light when it passes through the outer atmosphere of a star. The material in that outer atmosphere absorbs certain frequencies of light, and it results in these absorption lines in the spectrum. Due to the Doppler effect, these lines will get shifted. So if the star is approaching, it's going to be shifted toward the blue end of the spectrum. And if the star is receding, if it's moving away, these lines will be shifted toward the red end of the spectrum. So using this Doppler effect technique, you can estimate how fast the star is moving in which direction. And when you use this technique to look at distant galaxies, we found that those galaxies that were a certain distance away from our galaxy would all be moving away at approximately the same speed. And if you double the distance, looked at galaxies twice as far away, they'd be moving away with double the speed. This discovery showed that the universe was expanding. And not only that, running the clock backwards, you'd find that at one time all the galaxies were at the same location. And that time, of course, we call the Big Bang. That's the moment that the universe came into existence. So these two twin discoveries changed our view of the universe immensely. One of the things that everyone intuitively gets wrong with this is that how is it that everything's moving away from us? Doesn't that make us special? We're the center of the universe because everything's moving away from us? I thought that when I first heard this, but it's not true. And here's how to see why. Say we represent the universe by this two-dimensional grid of galaxies. Each one of these dots is a galaxy in a grid. And at the present time, we have this certain spacing, and then at some future time, we have a larger spacing because the universe is expanding. If we pick a galaxy, say this one, and we overlap the present and the future versions of that galaxy, you'll see that from the perspective of this galaxy, everything appears to be moving away. And the further distant the galaxy is from us, the faster it seems to be moving away. And so now, if you take a different galaxy, just pick any one, do the same thing, you find from this galaxy's perspective, everything seems to be moving away too. In a way, it's sort of like everyone's the center of the galaxy, or no one is. Okay, so let's take a quick timeline of what's happened since the Big Bang. So the Milky Way came into existence about 5 billion years after the Big Bang. So that took that long for gravity to coalesce matter into the Milky Way galaxy. And then some 4.5 billion years after that, our solar system finally coalesced. And then only about 1 billion years later, the first life appeared on Earth. As soon as the Earth was cool enough to allow for life, it popped up. Although that was microbial life. It took another 3 billion years for animals to come into existence. And that's, of course, including us. Right now, we're at 13.72 billion years after the Big Bang. That's now. I would put humans on this graph, but it's about 1% of 1 pixel, so there's no point. And notice, by the way, I show life only extending another billion years or so, and there's a reason for that. It's because our sun is aging, and what happens to stars as they get older is they get hotter. Every billion years, it's getting about 10% hotter. And this matters because the increased temperature of the Earth that results from this increase in luminosity of the sun will allow water vapor in the upper atmosphere to not freeze, and the Earth loses its water. The same thing happens to the Earth that happened to Mars. Mars used to have liquid water on its surface. It's now a dry planet, and the Earth will become a dry planet as well if you wait more than 1 billion years. And of course, our sun has only got about another 5 billion years left in it. It becomes a red giant and swallows the Earth at that point. There's a limit. There's a time limit. Oh, and also, there's something interesting that happens to the Milky Way galaxy, too, in the next 4 billion years. Because remember I said the galaxies are moving away? Well, there's some exceptions. Andromeda is blue shifted. It's coming at us. We are falling toward Andromeda, and it's falling toward us at a rate of about 300 kilometers per second. In about 4 billion years or so, we're going to collide. And so it's going to be quite a nice dance when we collide with Andromeda. It'll take a while for things to settle down. The two spiral galaxies will become one big elliptical galaxy. It's unlikely that our sun's going to collide with any other solar system. It's just that there's such vast amounts of space between stars. It's not likely that there's going to be a collision, but it could be that because of gravitational interactions, our sun could be ejected from the galaxy. But we have no way of knowing. We have a long time to decide, but we should decide on a name for this new galaxy. I'm not sure. My favorite is Andromeda. I don't know. We can vote later. Let's get back to general relativity. Remember the cosmological constant which Einstein added to make his theory consistent with a static universe. Well, now it's realized that the universe is not static, and Einstein actually regretted adding this to his equation. He called it the biggest blunder of his life. What is the ultimate fate of our universe? What's going to happen in the distant future? Well, there's 3 possibilities. One is that we live in an open universe. So if there's not enough matter in the universe to slow the expansion because of the force of gravity, the universe will just go on expanding forever. And eventually the stars burn out. The universe becomes cold and dark, no life. That's called a big freeze. If there is enough matter in the universe to slow the expansion and to cause it to recollapse, that's a closed universe, and the ultimate fate is called the big crunch, the reverse of the Big Bang. And there's a middle ground. If there's just enough matter to slow the expansion but not quite stop it, we live in a flat universe then. So how can we tell which of these 3 types of universe we live in? We can do it by measuring the overall geometry of space. Here I've represented 3-dimensional space by this 2-dimensional grid again, just so that we can imagine it. In a flat universe, one that has just the right amount of mass, the overall geometry is flat. This is the overall geometry of space, ignoring the local ripples that are caused by suns and galaxies. This is the big scale geometry. So in a flat universe, parallel beams of light are, say, parallel forever. And if you measure a large triangle, the angles of a large triangle, the angles add up to 180 degrees exactly. In a closed universe, one that's going to recollapse, the geometry is like this sphere. So the universe is curved in on itself. And in a closed universe, parallel beams of light will eventually converge, just like the lines of longitude will converge at the north and south poles. And if you add up the angles of a large triangle, it adds up to more than 180 degrees. And finally, in an open universe, one that just has enough matter to slow but not stop the expansion, the overall shape of space is like this saddle shape. Two parallel beams of light will diverge, and if you take a large enough triangle and you add the angles up, they add up to less than 180 degrees. So essentially, we can find out which universe we live in simply by measuring the angles of a large triangle. Unfortunately, it's got to be really large to actually measure this. So fortunately, the universe has got just such a triangle. It's as big as the observable universe. Imagine us here in the Milky Way galaxy. We're looking out in space. We're seeing all these galaxies that are billions of light years away. Not only are they billions of light years away, but we're also seeing them as they were billions of years ago, right? We're looking back in time because it takes light time to travel. So if we are able to look back in time far enough, you'd think that maybe we could see the Big Bang. And in principle, this is possible, but in practice, there's a problem because there's a wall between us and the Big Bang. Because as you look back in time, the universe is hotter and hotter. And at some point, the universe is so hot that all the matter is in a plasma state. And plasmas are opaque to radiation. You can't see through a plasma. So essentially, we've got this wall. And it's got a name. It's called the last scattering surface. So this is the point at which we can't see beyond. It's a prediction of the Big Bang model that we should be seeing light coming from this last scattering surface, coming from all directions. The expansion of the universe has redshifted this light. So now it's no longer light. It's actually in the microwave part of the spectrum. And it's called the cosmic microwave background radiation, or CMBR. This CMBR was detected in 1964 with this antenna. And these two men were credited, Robert Wilson and Arno Penzias. They got the Nobel Prize in 1978. They weren't even looking for the CMBR. They were doing research in microwave satellite communications. They thought this was just an interfering signal. Ever since then, we've been measuring this CMBR with greater and greater precision. This satellite is called the Wilkinson Microwave Anisotropy Probe. This has measured the CMBR with unprecedented accuracy, and after it was launched in 2001, it spent the next 7 years surveying the sky and came up with this picture. So this is the false color picture of the sky in the microwave spectrum. Why is this important? Well, the red spots there represent areas of the early universe that were slightly more dense than other areas. And this slight density increase represents lumps in the early universe. These lumps had begun to collapse due to gravity. And this gives us a triangle. There's the Big Bang on the right. We've got the last scattering surface that was formed 300,000 years later. And we've got this cosmic microwave background radiation coming from that last scattering surface. These lumps that are formed by gravity, since the universe is only 300,000 years old, gravity travels at the speed of light. The biggest lumps that could have formed are 300,000 light years across. That's as far as gravity could have traveled in the age of the universe. So we can expect to see that these lumps are only 300,000 light years across. When we measure how big these lumps appear on the sky, if they appear to be about 1 degree across in the sky, then we can conclude that the universe is flat. If the geometry of space is such that these lumps appear to be more than a degree across, then we live in a closed universe. And if they're less than a degree across, then we are in an open universe. If we look at the data from WMAP and we graph it, it's very clear. The peak is at 1 degree, and therefore the universe is flat. We now know we live in a flat universe after 50 years of science. And so we can basically just discard these other options, the open and closed option. But there's a problem, because now that we know that we live in a flat universe, it implies that there must be a certain amount of mass, a total amount of mass in the universe that makes the universe flat, that is slowing the expansion of the universe. And if we estimate how much regular matter there's in the universe, we've come up far short. There seems to be only a few percent of the mass necessary to make the universe flat. And the rest of it we don't know. We need a way of seeing the matter that is not visible normally. So here we have a picture from the Hubble Space Telescope. Every blotch you see in this image is another galaxy. This is an image full of galaxies, each with 100 billion plus stars. Now, most of these galaxies are pretty circular in shape, pretty regular, but there's some irregular bluish galaxies here. It turns out that these galaxies are really the same galaxy. We are seeing multiple images of the same galaxy because of this phenomenon called gravitational lensing. So in 1936, Einstein predicted that space could act as a lens, and that's what's happening here. That blue galaxy is actually on the far side of this cluster of yellow galaxies, and the intervening space is causing the light from the blue galaxy to bend, and we're seeing multiple different distorted images of that blue galaxy. This is interesting, but not only that, it's very useful because if we use some computer modeling, we can take those images and we can compute where in that galaxy cluster the mass lies. And so if we do this, we get a graph like this of the mass. And you can overlay the visible image where we see spikes of mass. That corresponds to galaxies in the visible image. But there's also this big mound of mass that all of these different galaxies are embedded in this mound of mass, but we don't see that large amount of mass that these galaxies are embedded in. This is the dark matter. There is missing matter that we can't see, and we do not yet know what constitutes dark matter. This is one of those things that could be addressed by the Large Hadron Collider. It would not be surprising in the next decade if we determine the nature of dark matter. And so that gives us some of the matter that we need to make the universe flat. Well, there's still a big unknown. Now we need another technique to try to find the missing part of the universe. This picture here, it shows a galaxy maybe with 100 billion stars. And in the bright core of that galaxy, it's about 10 billion stars. But there's an anomaly here. On the edge of this galaxy, there's what appears to be a star that's shining that's about as bright as the core of the galaxy. It seems to be shining with a brightness of about 10 billion stars. So what could that be? Well, that's a supernova. That's what happens to massive stars when they reach the end of their life. They produce a supernova like this one. Supernovae are fairly rare. They happen about once per century per galaxy, which sounds very rare, but just consider this. If you take a dime and you hold it up to the sky at about arm's length, that region of space, there can be about 100,000 galaxies in that region of sky. On any given night, you'll have 2 or 3 supernovae going off in that small region of space. And so with a large enough telescope, you can see these supernovae. And it's a good thing that supernovae occur because the Big Bang produces just hydrogen, helium, and a trace amount of lithium. It takes a star to forge all these other heavier elements, all the way up to iron. It stops at iron because iron takes more energy than it gives to fuse. So the star doesn't produce anything heavier than iron. If the star then goes supernova, all the heavier elements are created, and not only that, those elements are released into the universe to form future stars, planets, and people. Life on Earth and elsewhere depends on this process. And there's certain aspects of physics that are necessary for this to occur. So for example, if the force of electromagnetism was a few percent stronger than it is, it's possible that the fusion reaction would not occur. And of course, then there would not be any life because we just have hydrogen and helium. Our life depends on the physics being the way it is and the constants of nature having the values that they have. And this might be something that's important when we cut to the anthropic principle. So there's a certain type of supernova that is of particular interest. It's called a type 1a supernova, and it happens when a red dwarf star is in orbit around a white dwarf, and the white dwarf is stripping material off the red giant. Eventually, it gets up to 1.4 solar masses, and that's the point at which it detonates. and it goes off with a characteristic brightness. If you measure the period that the supernova lasts, you can determine its luminosity, and using the same technique as we used for Cepheid stars, we can use this as a standard candle to estimate large distances. And because this is so bright, we can estimate very large distances. And so we can estimate distances large enough that we can start to see how the expansion of the universe has changed over time. And everyone, of course, is expecting a decelerating universe. All three cosmologies, open, closed, flat, they all predict that gravity should slow the expansion of the universe. But when this experiment was performed, we found the opposite. Totally contrary to what was expected. The universe is accelerating, not decelerating. And the explanation for this is that, well, one of the explanations is that space itself, empty space, has an energy associated with it, the energy of empty space. It exerts a negative pressure and results in a repulsive force that causes the universe to accelerate as it gets larger. And interestingly, if we return to the general relativity, the cosmological constant, if all we do is take that constant, we throw it across the other side of the equation, change the sign, that would be a reasonable representation of dark energy. Turns out that maybe Einstein, even though it was for the wrong reason, he might be right after all. In fact, if he were alive today, he might even regret his earlier regret. And even when Einstein's wrong, he's right. It's amazing. Not only does this account for the accelerated expansion of the universe, but also it gives us the missing mass that we were looking for to make the universe flat. Now you say, well, it's energy, not mass, but mass and energy are equivalent, right, by E equals mc squared. So we may not know very much about what dark matter and dark energy are, but the puzzle pieces seem to be fitting in place at least. Now we have to modify this slightly because this graph presumes that matter dominates. And so in a flat universe, yes, the expansion of the universe slows. But when you have dark energy, now when that dominates, the expansion of the universe actually accelerates. Here's the next puzzle. Imagine if dark energy was much stronger than what we observe. Say it was 50 times bigger. In that case, no galaxies would form, because at early times, this repulsive force would cause the space to be driven apart, and the galaxies wouldn't form. Therefore, the solar systems wouldn't form, and planets wouldn't form, and of course, we wouldn't be here. We're lucky that we live in a universe that happens to have a low enough dark energy such that we can exist. So either we're lucky, or we have to invoke something like the anthropic principle to explain this. And now I have to explain what I mean when I say anthropic principle. Let's take the case of the Earth-Sun distance. We are lucky because we live in the habitable zone. We could look at it that way, right? That it just so happens that the Earth is just the right distance from the sun so that liquid water can exist and therefore our life is possible. But of course, that's not really quite the right way of looking at it, because it's not that we're lucky, it's just that there are billions of planets out there and we have to find ourselves on one that is compatible with our life. So that's essentially what the anthropic principle is. Our observations of the universe have to be compatible with our own existence. And we actually know approximately how many habitable worlds are out there because of this. This is the Kepler Space Telescope. It's staring at this region of space in our galaxy. For the past 5 years, it's been looking at this area, and it's been monitoring 150,000 stars. And what it's looking for exoplanets, but they're too far away to be directly detected. It needs this indirect method where it's monitoring the brightness of the star, and as the exoplanet passes in front of the host star, it causes a slight dip in the brightness because it's obscuring part of the star. So we're looking for these little dips. And when we see this happen multiple times, we can estimate how big the planet is and how far away it is from the host star. And there has been about 3,500 exoplanet candidates detected by Kepler so far. And here's a graph of all of their different distances from the star, and their masses. As you can see, this gives us a nice landscape of possibilities. And so all we need is a few planets to be in the region we consider habitable, and then the anthropic principle says that, well, we have to find ourselves on one of those habitable planets. There's no puzzle over why we find ourselves on a planet that's habitable for life. There's lots of possibilities out there. So before we get back to the anthropic principle, I'm just about to wrap up. There's a puzzle in physics that I have to explain, and that is that we have two very successful theories of physics. One is quantum theory, which is the physics of the very small, and there's general relativity, which is the physics of the very large. And if we try to mathematically combine these two theories, what happens is we get infinities. You cannot combine these theories and get a sensible theory that encompasses both large and small aspects of the universe. What we need is what we call a theory of everything, something that spans the entire range. And that's something we don't have yet. One of the candidates is string theory. And I'm sure you probably have heard of this. Here's an XKCD comic that summarizes it. I just had an awesome idea. Suppose all matter and energy is made of tiny vibrating strings. Okay, what would that imply? I don't know. So this is basically an acknowledgement that string theory hasn't yet to make any testable predictions. We don't really know what string theory's relationship to reality is. We don't really know if string theory reflects reality in any way. But in any case, this is how it fits in with the rest of physics. We have atomic physics, and it results in all of the elements in the periodic table. That's an unfortunate name, too, because in Greek that means indivisible. But of course it is divisible. They're composed of elementary particles. For example, quarks. We've had a lot of news lately. The Large Hadron Collider has confirmed the existence of the Higgs boson just last year. And this is Peter Higgs. He's 84 years old now. 50 years ago, he predicted the existence of the Higgs. He lived to get his Nobel Prize. Earlier this year, he was awarded the Nobel Prize because it was actually detected by the LHC. Okay, so string theory posits that maybe that's not the bottom. Maybe we can go one step further, and that perhaps these elementary particles are actually composed of these one-dimensional strings, which are essentially vibrations. But there's a bit of a trick here. You need more than the 3 spatial dimensions and the time dimension that we have. You need an additional 7 space dimensions in order to make the mathematics of string theory work. And now, how can you have additional dimensions? Well, they can be compact. Say we have this 2-dimensional space. If at every point in that 2-dimensional space, there's an additional short distance that you can travel at a right angle to your existing dimensions, you can have these curled up additional dimensions. And they could be of different shapes. Here we have spheres at every point. Here's another example where I've put a torus shape at every point in space. So you can have different physics result from different shapes of this curled up space. So with the 7 additional dimensions to work with, you can get some really complicated shapes. There's a whole family of different shapes called Calabi-Yau manifolds, and this is one example of it. With all this freedom, though, you can have a lot of possibilities. In fact, it's been estimated that perhaps there are 10 to the 520 possible universes that are approximately like our universe. Instead of a theory of everything, really, this sort of represents a theory of anything. What good is a theory that basically predicts anything? Maybe it is useful for something, because remember our landscape of possible different planets. It enabled our life, because there's some planets that are going to be conducive to our life when you have so many possibilities. Well, maybe if there is more than one universe, and each universe realizes a different possibility from string theory, then maybe there are some universes that are conducive to our life, and we of course find ourselves in one of them by the anthropic principle. And there's many other universes that have other constants, other physics, which aren't conducive to life. There's no one living there to observe that they live in a universe that's bad for life. So that's essentially the speculative theory of why there might be other universes. We may never be able to directly prove that this is true. There may be no test ever that other universes exist. However, if we at some point develop a theory of everything which we can test, and that does imply that there is other universes, then we might give this idea some credence. But until then, it's just a speculative idea. And with that, I want to finish up with another quote from the Hitchhiker's Guide. There's a theory which states that if ever anyone discovers exactly what the universe is for and why it is here, it will instantly disappear and be replaced by something even more bizarre and inexplicable. There's another theory that states that this has already happened. Thank you very much for your attention.